Now we're going to make a transition to another level of understanding ANOVA. These are more other ways of understanding ANOVA rather than levels so much. As we move into more complicated ANOVA models, the terminology changes some, contrasting changes a bit, the logic changes a bit. It's still the same logic of testing hypotheses, it's just that now that we move into more complicated models, we need more terminology to explain how to contrast the between to within variances. Okay, well, let's take the concept of factorial ANOVA. People differ over many variables. So people can differ in the type of the car they drive, their birth order, personality types. Many variables can stratify people, can define them, occupational categories, all kinds of things. And we're used to seeing those in studies. We're used to seeing where people with high and low cholesterol are people who exercise versus those who don't, or people that have different levels of exercise, or different types of diets that they're put on, then they're contrasted on some dependent measure. At any rate, we see this commonly, and people differ over many different variables and all kinds of things. You can manipulate people over different variables. So if you decide you're going to do an experimental study, you're going to manipulate a variable. You're going to structure it yourself as the researcher and not have it naturally occur. So you can tell people, okay, I'm going to do a study of sleepiness and performance in a memory test. And so you tell people, okay, I don't sleep for the next night or whatever, and come back in, and we'll test you on this memory test. And then you have other people who have been able to sleep. Common application, of course, is in testing new drugs, new medications. You put people on different dosage levels of a drug in contrast to a placebo, and you measure some dependent measure, like say it's a drug to pressure or a drug to treat infection or something. You have a dependent measure that reflects the status of that thing, of that construct. So if it's something that's testing blood pressure would be the dependent measure. Then you'd have different drug conditions, usually different dosage levels, that define the independent variable. And what you're doing is you're going to manipulate the variable yourself. You're going to administer different dosages to different people and control that variable. It will not occur naturally. Well, one way ANOVA, the structural model, the one we've learned so far, analyzes one independent variable at a time. And that's what we've learned so far. So we had birth order, as you recall, and leadership skill was our dependent measure. And we compared 3 birth order levels, and we had one independent variable. Well, imagine if you wanted to compare something like birth order and personality type, and with a dependent measure of leadership style. So there you've got to consider birth order and personality type in the same study. And now you've got 2 independent variables, birth order and personality type, and you want to find out if that's related to leadership style. Well, now you've transitioned to a much more complex model of analysis of variance, and that's referred to as the factorial model. So the factorial analysis of variance analyzes more than one independent variable at a time. It makes it different than the structural model that we've studied so far. So here's a little bit clearer statement of independent variables and dependent variables. So if you have a two-way ANOVA, indicating you got 2 independent variables, you're analyzing how one dependent variable changes as a function of 2 independent variables. So here's some examples. The independent variables are the type of car you drive and your hair color. Your dependent variable will be your driving speed. So an investigator in this situation wants to find out if type of car and hair color interact to produce a difference in driving speed. So a hypothesis here might be something like people who have red hair and drive sports cars drive faster than people with dark hair who drive sports cars. Or people with dark hair who drive sedans are different than people with red hair who drive sports cars. You can see where now you're combining the independent variables to make your predictions and your hypotheses. You're not dealing with them one at a time like you did with the structural model. So here, your state of arousal and alertness and the type of math problem that you get. So a state of arousal might be something where you're very alert and aroused and awake, And the type of math problem might be something as simple as just a difficult problem versus an easy one. Or it might be the type of math that's actually conducted in the problem, like division versus addition. Another example is word frequency and regularity and time to read the word. So if a word is very frequent and commonplace versus those that are rare words, that would be one independent variable. And regularity might be something that refers to how often the word appears in text and the time it takes you to read it. So presumably more difficult words that appear infrequently are going to be harder to read than words that are easy and appear all the time. And finally, we have another one here of stimulus, emotional tone, and gender. Here you have stimulus, emotional tone refers to things like pictures that have an emotional valence to them, like if you saw a picture, say, of a snake or something threatening to bite you. That would be something that would have a emotional tone to it versus a scene of, say, a scene of a countryside or something that doesn't have anything that's associated with emotions. And gender, obviously, is male or female. And the dependent measure might be your memory for those stimuli. So the investigator is interested in knowing if women remember more emotionally toned stimuli better than men do. And so the independent variables are combined, and we'll get to more detail of how that's done. But here we're going to be combining categories of independent variables, and they can be 2 independent variables, 3 independent variables, 4 or 5 independent variables. You can see where this can get pretty complicated if you have lots of independent variables with multiple levels for each one. Here are some new terms for us as a part of Factorial ANOVA, and we'll go over these again. This is just to introduce them. The first concept that's new is that of a main effect. Now, a main effect is very similar to what we studied with the structural model when we only studied one independent variable. The main effect is the effect for just the independent variable, just like in one-way ANOVA, and the second variable, or the third independent variable, is not considered. So suppose we were looking for birth order. Suppose we were contrasting birth order with gender. So we'd have birth order as one independent variable and gender as the other. Well, when we do our analysis, we'll talk about the independent effect for birth order as the main effect for birth order, and the independent effect for gender as the main effect for gender, as if we weren't even studying the other independent variable. So we're going to calculate our mean differences for the different levels of birth order and see if the difference could have occurred by chance, and that's going to be independent of the consideration for gender. A single independent variable being considered independently. Now, interaction effects are when we take the independent variables and interact them to see what happens. So here we'll be interested in testing whether firstborns who are females are different than secondborns who are males. So see how I've combined the independent variables? Well, these interaction effects deal with all these possible interactions you can have between the levels of your independent variable and whether differences in means associated with those could have occurred by chance or not. And those are referred to as interaction effects. So in Factorial ANOVA, you have main effects and interaction effects, and we'll talk about those in much more detail. Well, here we've got an example of a very simple two-way ANOVA, which we're going to use Factorial ANOVA to analyze it. This is a study that I did a while back that dealt with the adjustment of patients to traumatic brain injury dependent upon whether they had social support or not. So I was very interested in knowing what this relationship was between how disabled somebody was from a traumatic brain injury and whether that interacted with social support they had in their environment to adjust to daily living. I had observed clinically that patients that had poor social support, they didn't have families around to help them, had the worst outcomes. And it's nice to have family around who have things like businesses where you can get a job, or people that have money that can lend to you or help you with. And there's nothing better for going back to employment if you actually have a family member that owns a business where they can employ you, because they're going to be much more receptive to you going back to work after your traumatic brain injury, and they're going to really help you adjust better. So I was very interested in how generally that would influence adjustment to living in work environments if you had social support, but I also knew it would interact with your disability level. So patients that are very, very disabled after traumatic brain injuries aren't going to be helped much, even if they have a strong social support network. They're just so disabled they're just not going to be able to adjust to, say, a work environment. Patients will adjust to living in work environments independently of having social support because they're just not very disabled. And so they'll pretty much go back to what they were like before. Well, I was interested in how these two things might interact. And so here we have a model for how that might work. And I've substituted some imaginary numbers here just so to make the relationships clearer. So you have two independent variables. You have, and I've made them simplified, you have patients who are unimpaired. So they've had their traumatic brain injuries, they're not impaired, versus patients who come from their traumatic brain injury and they're quite impaired and disabled. So that's the independent variable you see there on the left. Then up at the top you see social support as an independent variable. So you have patients with a lot of social support versus those with no social support. And here you see sort of a theoretical statement of what their levels of adjustment to living might be after their injury. So my dependent variable is adjustment to living in working environments, and that's represented by those numbers. So we look across the table there. If you look for just the main effect for disability status, you just compare patients who are unimpaired to those who are impaired, regardless of what their social support is. And you can see that out there on the far right is a marginal distribution of levels of adjustment. So the unimpaired brain trauma patients have a adjustment to living in work environment score of 28, and the impaired patients have an adjustment to living in work environment score of 15. So that's the main effect for impairment status. Then if you look at the social support, you see that patients with social support tend to have a score of 25, see at the bottom of the column on the left, and those without social support on average have a score of 18. Now, as you look within the cells, you can notice that there's change there. There's not an even distribution of values within those cells. There's something about them reflecting an interaction probably between impairment status and social support. Now, if you look at people who are unimpaired, these are people who are not disabled after their injury, who have high levels of social support, they have a 30, which is the highest score in the table. And that makes sense. People who are not impaired but have good social support, they should have the best outcomes. They're not that disabled, and they have strong social support mechanisms. Now, if you're unimpaired and you don't have social support, your number's lower, but it's really not that low. Basically, if you're unimpaired, you pretty much fall back into your old pattern of living and work, and you don't need social support to help you elevate it. Now, if you're impaired, and these are the folks that we're really concerned about, if you're impaired and you have social support, 20, which is still lower than those who are unimpaired, but notice that it's still much higher. It's twice the level of impaired people who have no social support. So social support really works when you're impaired. It becomes a major factor in determining your adjustment after your head injury if you're impaired. Now, see how those things interact? There's not just main effects here. There's now an interaction between being impaired and benefiting from social support. If the results came out this way in the study, and they were statistically significant, I would conclude that people who are impaired benefit more from social support than people who are unimpaired. And if you're impaired and disabled and you don't have social support, you'll have a very bad outcome. Now that's how factorial models, and this is a very simple one. This is just two levels on two independent variables. Imagine if I had 5 or 6 levels on these independent variables, and imagine if I had more than just two independent variables, how complicated these tables could get. But here's how the factorial model works. You're basically looking for independent variables and how they interact, and you have one dependent measure that you're going to compare. Okay, here's another example of factorial ANOVA of another study that I did. And in this study, we're interested in whether the emotional tone of pictures and words would influence memory for those things. So here we've got, and we're interested in gender effects. So here we have gender and emotional tone as our independent variables. And here you see on the bottom left there a very emotionally toned picture, a dog, growling at you. And then the bottom right you see one that has no emotional tone. It doesn't really engender any feelings one way or the other. And so we presented sets of these pictures. We actually presented these in the MRI scanner to find out if there was different parts of the brain that were used to remember emotionally toned versus those that were not. But we also measured the number of pictures they recalled. So how many do they remember? Now you might imagine a very simple hypothesis would be that emotionally toned pictures were remembered better than those without emotional tone. But this is the basic setup where you've got two independent variables and one dependent variable, which is going to be the number of pictures they recalled after seeing sets of them. Okay, let's deal with the possible results of this study for a two-way ANOVA. So I've got two independent variables, one dependent measure. Well, here's the first result I could have, which would be an interaction. So when it comes to memory for pictures, emotional pictures and neutral pictures show the same level. You can see where it's different. Emotional pictures are a 40, neutral pictures are a 50, but presumably that doesn't reach statistical significance. That could have occurred by chance. And here we see that gender also does not show a significant difference, so that men and women are recalling approximately the same, even though there's a different number. Since it didn't occur, it's not statistically significant. It could have occurred by chance. Now the interaction represents gender being related to the recall of neutral pictures, so that women are recalling a large number of neutral pictures, but everyone else is recalling roughly the same. Now you can see where, look at that in the internal parts of the table, you can see where emotional pictures are recalled equally by men and women. See, there's 40 and 40. And men are recalling equally emotional pictures versus neutral ones. But women are really recalling neutral pictures at a much higher level. And that's what's producing the slight differences across the main effects. But when you look at that internal table, you see that they're all the same, except that for women and neutral pictures, there's some sort of special confluence there of influence, and you see a big difference in the dependent measure. But that's what a pure interaction looks like. Here's another type of interaction. This could be another result of the study, and it represents another interaction between the two independent variables. Among men, emotional pictures are remembered better, and among women, neutral pictures are remembered better. Now notice that the main effects result both in 50 and 50 for each men and women, or emotional pictures and neutral pictures, but within that table you see there's discrimination. Whereas men remembering emotional pictures much better than neutral, and women remembering neutral much better than emotional. And that would have been masked if you just did a regular old structural ANOVA and just studied effects for each independent variable separately. Here we're showing an interaction that's quite interesting, and obviously is much more information than if we just compared the main effects by themselves. Here's another possible result of the study. You could have a main effect for gender and no interactions. And here you've got women remember more pictures regardless of emotional tone. So here you have the contrast of men and women. You see the men are at 30, the women are at 70. And emotional pictures and neutral pictures are roughly the same. And you notice that all the in between, referring to the emotional neutral tone of the pictures, are reflecting the fact that there is a gender effect and not an effect for the tone of the pictures. So here you've got a difference between men and women in regards to the tone. Men, if you look down the column there, men are remembering 20 emotional pictures and 40 neutral ones, and women remembering 60 emotional pictures and 80 neutral ones. And you can see the ratio is roughly the same. So across the board, there is no main effect for the type of picture. It's only reflecting a difference across men and women. And here you have another main effect. Here you have the main effect for emotional tone of the pictures. So the neutral pictures are recalled better regardless of the gender. You can see that very clearly where men and women do not differ. See, there's 50 and 50, but there's a main effect for the type of pictures. So neutral pictures are remembered better by 80 to 20. Here's another possible result, another interaction. Only women remember more neutral pictures. Men and women are not simply different in memory for emotional pictures. You look along the table there, you see that women are remembering many more neutral pictures. So here you see 80, and notice that the others are roughly remembering. So you have 60, 40, and 40, which is very much lower than the 80 there. And notice the marginals, especially for emotional and neutral pictures, do not show an effect. And it appears that men and women are remembering more pictures overall, but when you take into account that it's the neutral pictures that's producing the result, it's clearly an interaction, and the main effect may or may not be there. Okay, now that we have a sense for the possible results of a factorial ANOVA study, we're now going to go through the basic logic of calculating the F statistics related to the factorial ANOVA. Now, the basic logic is the same. Okay, you're always going to be contrasting the within subjects variability to the between subjects variability. There's always going to be that contrast. The degree to which the between is greater than the within will be a measure of whether or not the probability of the result is going to be chance or not. Because the between is very large, that means that one of the means has to be very different than the other means, at least one of the other means. And if the within subject's variability is small, then it's unlikely that those differences between means could have occurred by chance. So the logic is basically the same. You're contrasting the differences between means to the variability that's within the samples. If the F ratio is sufficiently high, if that ratio is sufficiently large, then the probability is that one of those means is significantly different from at least one other mean. Okay, so that's basically the same logic as existed before with one-way ANOVAs and structural models. So here we see a graphic depiction of this. Here you have the estimates of variability that come from the within factors and the between. And here you see there's one group that's different than the others. And the distance of that sample mean to the other sample means is really large. And so the between groups variance associated with that, because remember you calculate the between groups variance is a distance from the sample mean to the grand mean. And if all these other five groups are the same, then the sample means and the grand mean for them is going to be roughly the same. There's not going to be a distance from the sample mean to the grand mean for them. But the grand mean here is going to be pretty far off from that one that's separate. And so the between groups estimate based on that will be large. And if the within variability is relatively small, then that between difference was unlikely to occur by chance. If there's a lot of variability within samples, then mean differences across groups are relatively common. If that within groups variability is small, though, mean group differences across samples are going to be unlikely to occur by chance. Any mean difference that you see there is probably a result of design and not by some chance factor. However, there's a new way of looking at factorial ANOVA, a new way of looking at the between to within comparison. And here it is. There are 3 F ratios in two-way ANOVAs. As you might expect, there's an F ratio for the main effect for the column variable. There's an F ratio for the row main effect. And there's an F ratio for the interaction. Now this is common to all factorial ANOVA, that you have main effects and you have interactions, and you have separate F tests for these. So in this case you see here the old study of the patients who had traumatic brain injuries who were impaired or unimpaired, having high levels of social support or no social support. And what you're going to get is an F ratio for the column, which would be social support, an F ratio for the row main effect, which would be impairment level, and an F ratio for the interaction between social support and impairment level. Here you see the relationships in graphic form. So again, there's an F ratio for the column main effect, for the row main effect, and for the interaction. And here in this graphic, which is very similar to the ones you see in your textbook, you see the main effect, for example, for the column, which was social support. You see that represented as a contrast between the two pairs of graphs down below, where you have support on the left and no support on the right, and you get a feeling for how large the effect is by averaging all those. The disability effect, the main effect, is represented by the two different colors. So you have the light blue contrasted with the maroon, the purple there. Now you could have graphed these the other way so that social support was depicted by the colors. It doesn't really matter. The interaction is shown by asymmetry in this graph. And you can see there's asymmetry in the sense that the purple on the right is much lower than the purple on the left, but the two blues are pretty close. And that represents a disparity. It represents a kind of interactive dissociation. So it indicates that disabled people are especially affected by not having social support. And you would need to test that statistically, but that's what the interaction would look like in a graphic. If there was no interaction, then all these bars would be, these columns here would be, have the same relationship to each other. So the asymmetry that you see across those two colors wouldn't exist, and they would look like they were the same. They would appear the same, even though one might be a little bit lower than the other. Their relationship to each other would not be asymmetrical. It would be in proper proportion. So now we'll go through the column main effect in more detail. Here we have social support versus no social support. This is the column main effect. And you can see the numbers that represent each cell in that effect. And we're just going to test whether having social support or not having social support produces a statistically significant result. Is the 25 there different than the 18? Or could those numbers have occurred by chance? And here we see the column main effect in graphic form. So we have row main effect is here as well in terms of the columns on the left there. So there you see unimpaired, where you have support, they have a 30. We have no support, they have a 25. If they're disabled, if they have social support, they have a 20 for the dependent measure. And if they have no support, they have a 10 for the dependent measure. Now we're just going to check the column main effect for support or no support. So we average across those. So again, somebody on average, if they have social support, regardless of their disability level, they'll have their dependent measure will be a 25. And if they have no support, their dependent measure will be an 18. And we're going to check to see if that difference could have occurred by chance, or is it likely not occurred by chance and represents an effect of social support. Okay, now we're going to do the row main effect. And the row main effect is done the exact same way as the column main effect, but obviously it's going to be a different set of numbers. And here you see them depicted here. The row main effect is for disability level, and you're testing the hypothesis about whether someone who is unimpaired after their brain injury will do better or worse than somebody who's impaired after their brain injury. And here you see the numbers. You see on average, if you're unimpaired, your dependent measure is a 28, which is relatively high. But if you're impaired or disabled, on average, your disability level is a 15. Now, given the magnitude of those numbers, just eyeballing them, it looks like there is a main effect. But again, we have to test it statistically. We don't know if that result could have occurred by chance or not. And so that's what we're going to do. Okay, here we see the row main effect in graphic form. So you have the main effect for support, no support in the column chart on the left over there. Then the colors reflect the impairment status of the patient. So the disabled patient, they're represented by the purple, the maroon column, and the unimpaired patients represented by the blue. And on average, people who are unimpaired have a dependent measure of 28, I believe that was. And then people who are disabled on average have a score of 15. Now you can see a big difference there. I can't imagine that doesn't come out statistically significant. And it indicates that there probably is a row effect for being disabled, which makes a lot of sense. If somebody's disabled, their outcomes are poor in general. No matter what their social support is, they're going to have a worse outcome if they're disabled than if they're unimpaired. Now we have the tricky part, the part of Factorial ANOVA that's the new introduction here. And this is the statistic for the interaction. So the interaction is the new thing we're adding with Factorial ANOVA because now we have more than one independent variable. So we have an independent variable of impairment status, being unimpaired or impaired, an independent variable of social support, having social support versus not having it. And now we want to find out if there's an interaction between these two variables. So you see here depicted in the two different colors, the unimpaired people with social support have a 30. The impaired people with no social support have a 10. And see that's a big contrast. There's a big difference between people who have an impairment level of a certain value and a social support level of a certain value versus people that are impaired and disabled who have social support versus those who are unimpaired with no social support. You can see where that 10 sitting down there is an especially low number and reflects a strong interaction between impairment level and support. Now, we've seen before that there probably are also main effects for social support and main effects for disability status that are independent of this interaction. So in other words, in general, if you have social support, you do better than if you don't have it. And if you're unimpaired in general, you do better than if you're impaired. But if you're impaired and you have no social support, you do abysmally poor. You do far worse than any other group in the study. And this interaction tells us to see if that could have occurred by chance, or does that represent an special interactive group that has an especially poor outcome compared to the others. Okay, let's deal now with the within subjects estimates of variance. If you look at this table here, you see each cell has variance in it, and the variance represents the distances of individual scores from individual subjects from their sample cell means. So you see under social support unimpaired, you see there's a mean of 30 plus or minus 4. And you see in the next one there's no social support unimpaired, a mean of 25 plus or minus 4. And so on, plus or minus 5, plus or minus 6. These represent around that number 30 or around that number 20. That represents the dispersion within the cell. So subjects that are within that cell don't exactly have the mean. You know, they say, let's go to the social support unimpaired. They don't all have a score of 30. Some have a score of 25, some have a score of 35, some have a score of 32, and so on. On average, it's a 30. But around that 30 is dispersion. And that's the within group, the within subjects variance that's calculated as part of the F ratios. So when we actually get to the point of calculating them, which we will in a little bit here, you'll see how this works in more specific terms. But the point is that within each cell, there's variability around the mean that's in the cell. And this is the same concept as the variability around the sample means that we studied before for one-way ANOVA. Okay, let's deal with conceptually how we calculate factorial ANOVA components. The first thing we want to remember is that there's a grand mean, and that's the mean of all your scores. So that's a reference point for all the deviation measurements. So all the variance calculations we're going to make all eventually refer to the grand mean. Now the deviation of an individual score from the grand mean is composed of the following elements. The first is the score's deviation from the mean of its cell, and that's the within group variance. Now you can see here we're still contrasting variance across cells to variability that's within cells. And that's the same thing as we did before with one-way analysis of variance, where we contrasted between group variance to within group variance. It's just that before with one-way analysis of variance, all the cells, what you'd call a cell, was also a sample. It's just that now we're going to break the samples up into cells, and we're going to treat them all individually. Okay, so the first thing we calculate is the score's deviation from the mean of its cell. The next thing we calculate is the score's row mean, from the grand mean. Okay, so the row mean is going to be the variability that's accounted for by a row effect, a row main effect. So we calculate the score's row mean from the grand mean, and that's the row between group variability. So that's going to be the row main effect. And now we're going to calculate, next we're going to score's column mean from the grand mean, and that's going to be the other main effect, the column main effect, and that's the column between group variance. And then, fortunately, we don't have to calculate the interaction because it's going to be what's left over. So if we have the total amount of variability in the study, which is going to be the distance of the grand mean from individual scores, and we subtract out the within cell variance, the row variance, and the column variance, whatever's left over that we subtract from the total variance is the interaction between group variance. So now what we're looking for again are F statistics for the row effect, the column effect, and the interaction effect. And we're going to contrast the deviations, the variance associated with the rows and the columns in the interaction to the within to get a ratio. If that ratio is large, that means that the difference between, say, patients who get social support and those who don't, as a column effect, that's large, and it's so large that it circumvents the noise associated with within group variability. It's bigger than that. And by probability, by chance then, it could have occurred. But if we do our analysis and discover an F ratio that's large enough, we can conclude that based on probability, this likely did not occur by chance. This big difference that we see for social support is probably something that's real. It's something that's out there in the world, something by design, and didn't occur by chance. And that's the power statistics give us to analyze data like this. We can then make our inferences based upon strong probability judgments and not just simple differences across groups or across cells and things like that. Okay, here's another factorial ANOVA example. A researcher was interested in men and women's ability to navigate using two different kinds of directions, following a map versus routes. So a route is when you give somebody directions verbally with no map. Navigation ability was measured by the time to reach the destination in minutes. At the p less than 0.05 level of significance, were there any main effects or an interaction? And over here on the right, you see the data for the subjects. You see that we have map reading versus route following for men and women, and then we have a dependent measure is minutes to reach the destination. You see, for example, that in the first cell up there, this is an individual subject cell, the first male, it took him 30 minutes using a map to follow find a destination. The woman on the same row took her 47 minutes. And as you look down those columns, you can see what the raw data looks like. Now you can also see that when you look in trying to compare, say, men versus women or using maps versus routes, you can't do that unless you actually analyze this data. It looks like there might be an effect there. You can see the numbers down below are smaller generally than the numbers up top, but all that could have occurred by chance. But when you analyze this statistically, you're going to be able to figure out, well, did this occur by chance, or is this something a real meaningful difference between men and women using maps versus following routes by directions? Now let's take this through the steps of hypothesis testing as presented in your textbook and what you've learned before when studying t-tests and one-way ANOVA. Okay, step number 1 is restate the research question. And you want to restate it in terms of populations. So now we're going to state this also in terms of factorial ANOVA. The first statement we have, the first set of hypotheses, is that we have a main effect for gender. So our null hypothesis is the population of men and the population of women will be the same. Their mean value for finding a direction by using routes or maps will be the same. Our research hypothesis, our H1 there, is that the population of men and women are different. And we might even have a theory that explains that men will be better or worse than women based upon maps or route finding. So thus far we haven't been presented with a theory. If we want to just make up one, we can just say that women are, since they're supposed to be better with verbal information, we'll say they're going to be better with routes, and men will be better with maps. But who knows? The next set of hypotheses govern the main effect for direction type. So we have a null hypothesis here, an HO, that using a route will be the same as using a map. Across the board, it won't make any difference whether you have a route or a map. People will perform the same. And then our research hypothesis is that they will be different. Now, stating that they're just going to be different, of course, if you think back on it, of course, is a two-tailed test. And You just have to keep that in mind. We haven't got to that point yet where we're mapping out the tails of a test. But right now, if we don't have a direction to our hypothesis, then we're looking for a two-tailed test. We're just going to say they're different. Not that one is better or one is worse, but that they're just different. And then finally, the new thing about Factorial ANOVA is we have hypotheses that deal with interactions. And these look pretty complicated. Now look at this null hypothesis for the interaction here. The population of men using routes minus the population of women using routes will equal the population of men using maps minus the population of women using maps. Now, you see how that works? We're basically saying that all things will be equal. It won't matter if there will be no unique cells. In other words, there won't be a set of men who are using maps that are exceptionally different than anyone else, or a set of women who use maps, or men who use routes. All the cells will essentially be equal. Now, the research hypothesis is that there will be a difference, that one of these cells is going to be different than the others. So the population of men using routes minus the population of women using routes will not equal the population of men using maps minus the population of women using maps. There's going to be some difference there that stands out, and we're going to be able to test that statistically to see if it occurred by chance or not. And that's the unique thing about Factorial ANOVA, this introduction of an interaction between the cells, where you might find that there's, for example, no main effects, but there's an interaction. Or you can find out there are main effects and interactions. But the idea is that there's special cells within this network of contrasts that are showing up different than the main effects, that they're just the row and column effects. Step number 2 is to determine the comparison distributions. And here we have 3 F distributions. Remember, in one way, we just had one F distribution, and that was essentially for a main effect. Now we have more than one main effect, so we need different F distributions for that, and we need the F distribution for the interaction. So we need to calculate also our degrees of freedom. And here you have degrees of freedom for each cell. So degrees of freedom within is the sum of the degrees of freedom for each cell. And here we have n minus 1, n minus 1, n minus 1, n minus 1. Remember, there were 4 subjects in each cell, so that gives us a degrees of freedom within of 12. Now we have degrees of freedom for our first main effect of gender. So that equals the number of genders, which are groups, which is 2, minus 1, which is 1. Direction type is map versus route, so there's 2 of those. And that's subtract 1 from that, and you get 1. And the degrees of freedom for the interaction is going to be the number of cells minus degrees of freedom for the main effect minus the degrees of freedom for the direction type. And so you do all that. You start out with the number of cells. There's 4 minus 1 minus 1 minus 1 equals 1. So the degrees of freedom are 12 and then 1, 1, and 1. Now this is a relatively easy example, and so you have degrees of freedom that are relatively small for the main effects because we just got 2 conditions, either male or female, or direction type being map reading or route finding. Okay, so we've got our distribution mapped out here as 3 F distributions with degrees of freedom matching these numbers. And now we need to determine our cutoffs. Well, we've already chosen the P level of 0.05, so that's our probability cutoff. And if you go look up the F you need for this, you look this up in a table. Now, when you run SPSS, of course, SPSS will calculate this directly. But when you look it up in the table, you'll discover, tables like we had before for the F statistic. You go look up for your p-value, you look up for your degrees of freedom, and then it will give you a cutoff score, a cutoff F value for that p level. So the tables are usually divided up into 0.05, 0.01, and 0.1. And here we've chosen the 0.05 set of numbers. And when we do that, with an F ratio in the denominator of 1 and an F ratio in the numerator of 1 and degrees of freedom from the denominator of 12, so we look that up for 1, 12, we get an F score cutoff of 4.75. So if our F ratio turns to be 4.75 or higher, then we have beat chance. We beat chance at the 0.05 level. Then it's unlikely that this result occurred by chance, and we have a cutoff of 0.05, a 5% chance of being incorrect, but that's relatively small. Now you can choose a p-value of 0.01, and so you can be more accurate, and then of course the f-score cutoff will be higher. But here at 0.05, which is conventional for most research studies, we have an f cutoff of 4.75. So when we actually calculate things with this sample, we're going to be looking for an f-score of 4.75 or higher. All right, step number 4 is to actually determine your sample scores on levels of these things. So actually calculate the means and calculate the f-statistics to find out if we can make an inference. Okay, to do this, we're going to do it in sort of 2 steps here. One is to use an Excel spreadsheet, which has these data in it and has the analysis worked out. So you can sort of see step by step or all the intermediate part to it. And then we're going to do it with SPSS. The downside of using SPSS is that SPSS never shows you what it did to generate the f-statistics. It just shows you the results. Whereas a spreadsheet will have all the data in it and all the means in it and things like that, and will show you the results that way. So step number 1 is go to the Blackboard website, go to the course website, and download a file called Gender and Directions Excel Spreadsheet. And take a look at that spreadsheet. Have it open with this presentation so that we can follow them together. Then also download a file called Gender Directions or genderdir.save. It should be called something like Gender and Directions SPSS data file. So both of those are downloaded. You can open it up in SPSS and have all 3 open at the same time. So you should be able to have this presentation, Excel open, and SPSS open, showing all these files. Don't run the analysis in SPSS yet. We want to do that together. But just have it available so we can go back and forth between each one. Right now, first we're going to look at the Excel spreadsheet. Okay, let's look at the Excel spreadsheet. Now you notice in this Excel spreadsheet, each cell is color-coded. So the men in the top left there, the light blue, that represents the cell of men who are using maps. And you can see their scores there of 30, 35, 33, and 42. Then the cell on the right is women using maps. And then below them is women using routes. And below that is men using routes. So you see how the numbers have been represented there in those boxes within the color-coded cells. Now, if you look around this spreadsheet, you can see where everything calculated that corresponds to what we've discussed so far. The sum of squares total, the sum of squares within, and so on. The degrees of freedom are there. The mean squares within the row, and so on. Now, the mean squares are where you estimate based upon the population degrees of freedom. And then we have our f-statistics over there in the far right down below. Now, what's neat about a cell spreadsheet, of course, is you can play with different numbers. You can click on a cell to see where the numbers came from, how they were calculated. You can change the values and see how that affects the numbers. You can do all kinds of things with Excel spreadsheets. It makes it very interactive. Now, if we look around here, we see that, let's look at the grand mean first. The grand mean is in the bottom left over there in the pink. The grand mean is 29. So the grand mean tells me that 29 minutes was the average it took anyone to do any kind of destination finding. And we're going to make all of our other calculations relative to the grand mean. And let's go to the cell up top, the light blue one, and go to column 2 in that cell. Now you can see that the first thing we're going to do is subtract the individual score, which is x, from the grand mean and square that. Now notice the first person's score was 30, the grand mean was 29, so that's 1 squared, which is 1. The next subject's score was 35, and subtract that from the grand mean of 29, that's 6, so 6 squared is 36, and so on down the column there. The next column represents the deviation of the individual score from the mean of this cell. Now the mean of this cell is 35. You see that in the bottom left corner of that cell. You can see where the mean value for all those 4 subjects is 35. So you do the same thing. So you take 30 minus 35. That's 5 squared is 25, and so on. And if you click on the cells, you can see where these things were calculated. You can see how Excel formulas are constructed. Then the next column over is the mean of the row. And see, the mean of the row is way over on the right side, where the row ends, and the mean of the row was 37, minus the grand mean squared, see for each subject. Then we take the mean of the column, mcol, which was 30, and do the same thing. Subtract that from the grand mean and do all of our subtraction. Notice that those are all our ones. The mean of the column was 30, and the grand mean was 29. So the difference for everybody was a 1. And notice that all those, for when you're subtracting the mean of the rows and the mean of the columns from the grand mean, you get the numbers. You're just permuting them for every subject you have. Now that process I've just described is repeated in every cell. The cell on the right over there has this calculated. The cell on the bottom left and the bottom right have also this calculated. Okay, let's go to the bottom part of the Excel spreadsheet now. Go below where it says the grand mean. Now click on the cell called sum of squares total, and you'll see that that's the sum of the, here it's C10, I10, C18, and I18. And if you look at those cells, C10 is the total sum of squares for the difference between the score and the grand mean. We summed all those up. Then the sum of squares within is going to be the sum of squares of the score from their individual cell means. You can see if you look at D10, that 78 represents the sum of square differences of the individual scores from the mean of that cell. Then the sum of squares for the row is going to be the sum of the row mean of the row minus the grand mean squared. See those 72s up there, 72.25 and so on. That's going to be 289 for that sum, plus 289 plus 289 plus 289. They all happen to be the same distance from the grand mean. Okay, well then you've got the column sum of squares, which is the same thing except it's done for the column mean. The sum of square differences of the column means from the grand mean. And notice this number is very small. This suggests that the column means are not very different than the grand mean, which means that they're not that different from the trend of the subject as a whole. And it suggests there's probably not going to be a column effect, but we'll have to see. And then finally, the what's left over is the sum of squares attributed to the interaction, which is 196. Now we calculated our degrees of freedom just like we did in the other slide. So we have 12, 1, 1, and 1, and 1. And then we calculate our mean squares, where we divide the sum of squares by the degrees of freedom. The mean squares within is the sum of squares within of 306 divided by 12, which is 25.5. The mean squares for the row is the sum of squares for the row divided by the degrees of freedom for the row. And you can see that's 1,156. Then you can see the mean squares for the column is 16, and the mean squares for the interaction is 196. Well, with the mean squares for the row being so gigantic, you know that that's going to be probably a significant effect. And sure enough, when we calculate the F-statistics, when we calculate the ratio of the mean squares row divided by the mean squares within, we get the number 45 for our F-statistic for the row, and that's a giant F-score. Then the F-score for the column is 0.62, which is very small, and the F-score for the interaction is 7.68, which is probably statistically significant. I think our cutoff was 4.75. So it tells me that the row difference, the difference between using a map and using a route, is really big. And if you look at the mean for using a map, that mean is 37 minutes, and the mean for using a route is 20 minutes. So there's a big difference, and that F ratio reflects that big difference. So it's unlikely it occurred by chance, this difference between using a map and using a map versus a route. Finally, there's an interaction, though. A 7.6 F there is higher than our cutoff of 4.75. And so now we've got to look at what means might have been different. And it appears that the women who use routes were much faster than any other cell there. You can see where their mean was 16 minutes, and all the other means in the cells range from 25 minutes to 40 minutes. So this suggests there's an interaction with women using routes outperforming every other cell. Now we're going to use SPSS and see what SPSS shows us. I sure hope it'll be the same thing. Now we're going to do the same analysis with SPSS. Go to your desktop or wherever you downloaded the file genderdir.sav and open it up in SPSS. You should have this presentation open along with SPSS open, and it should show a display something like what you see here in the slide, where you have a set of data, one column for gender, this has been coded a 1 or a 2, one column for the kind of directions they used, either a map or route finding, that's also been coded a 1 or a 2, and the third column is a dependent measure, and that's the amount of time, the number of minutes it took them to find a destination given a map or a route finding. So this is the first step. You should see a data file that looks like this. If you don't see this, or SPSS doesn't open, you've got to go through the steps of running SPSS and making sure that you've got the right version and so on. But if all goes well, you should double-click on the file or open up SPSS and open this file, and you should see a display that's like this. Okay, next we want to run the analysis. To run the analysis, you're going to choose the Analyze menu. So click on the Analyze menu. Choose General Linear Model Univariate. So this is the procedure you should follow. We're doing a univariate analysis of variance. It's called univariate because we don't have multiple dependent measures. We haven't got to that concept in the course, but that's why it's called univariate, because we just have one dependent measure. Okay, so choose Analyze General Linear Model Univariate, and that will enable us to run this analysis. After you run Analyze General Linear Model Univariate, you'll see a dialog box like this. Now, all these three variables, the three variables are time, gender, and direct, will appear in the left window. You want to put them in the right windows just like you see them here. So click on the variable time, the name of it, then click on the little arrow that puts time as the dependent variable. Then click on the name gender, and click on the arrow below the one that's for dependent variable. Indicate you want gender to be a fixed factor. Remember, this is factorial analysis of variance. Then click on the word direct, and also click on the same arrow, which makes it also a fixed factor. Once you get the variables in the dialog box looking like this, click on the OK button, and SPSS will run the analysis. Okay, if everything ran okay, you should see an output from the analysis that looks like this. Univariate analysis of variance. The first table will show you between subjects factors, so it's just telling you what the factors were. And then the table below is showing you the results. Now, an important thing to keep in mind is SPSS will report a lot of numbers and a lot of results that you aren't familiar with. Don't let that daunt you. SPSS generates a lot of extra statistics and things that people like to see, but many of these things are not pertinent to the, or germane to the analysis. They're things that help you interpret it, but they're not the basic F statistics and things like that that you need to see to make inferences. Okay, well, the top table gives you a check on what you did. Now you can sort of double check that you have the right number of subjects, they were coded correctly, and the data looks like it should, and this data does look like it should. We have two factors, gender and direct. We have male and female. We have 8 subjects in each cell. Okay, the bottom table is results. Now you can ignore the top 2 lines and go right to where it says gender. Now notice that it's the sum of squares for gender is 16, degrees of freedom of 1. Now remember, we can look that up in our Excel spreadsheet and see the same thing. The factor direct, which is the type of directions they got, map finding or route finding. Remember, the sum of squares was 1,156, that really big number. And you can see the degrees of freedom was 1. And the interaction of gender by direct, the residual sum of squares for that was 196. So that was the same as our spreadsheet. Now, SPSS refers to the within cell, the within subjects, or within groups sum of squares as error, and you can see that there is 306 with degrees of freedom of 12. The next column over, past degrees of freedom, is the mean squares, so that's the values of the sum of squares divided by the degrees of freedom. And so you can see down there, for example, gender of 16 divided by 1 is 16. if you go down to all these others, since our degrees of freedom are 1, the numbers should be exactly the same. The error, however, which is the within groups sum of squares at 306 is divided by 12, which is 25.5, which is also the same as in the spreadsheet. And now we go to the F scores. So the F is the ratio of the between to the within. And you go down the column here, say for gender, for the main effect of gender, we see an F of 0.627. That's the same as the spreadsheet, more or less. And that's insignificant. Remember, our cutoff was, I think, 4.75. For the type of directions, you see that monstrous F score of 45. That's very large. And then for the interaction, you see the same F we got in the spreadsheet of 7.686. Notice that SPSS does not give you a cutoff for F. Now, you use cutoffs for the F score because you're using tables. If the tables were produced that had every F score in it for every probability level, the tables would just go on for pages and pages and pages, and it wouldn't be a lot of relevant information anyway. But what SPSS does is actually gives you the probability associated with your F score. And your cutoff, it pertains to the P level of 0.05 rather than to a cutoff score. So if we look at the last column over here, the significance level, we see that an F of 0.627, which is the first one we're interested in, is associated with a probability of 0.44, and that's way above 0.05. And so that likely occurred by chance. The next one down is a very highly significance level, 0.000. Now that would be reported in your paper or whatever as 0.0001. So the probability is so low, it's very unlikely this occurred by chance. It probably was by design. And you can see that it's a highly significant result. The next one is the interaction. The interaction gives us a significance level of 0.017. That's below 0.05. And so we conclude that that also did not occur by chance. So just like we did with the spreadsheet, we discovered that there's a main effect for the type of directions, and there's also an interaction. Now notice for the interactions, you've got to go back and look at the tables to find out what the mean values were for each cell to make a deduction about which one is representing the interactive effect. In our case, I remember it was the women using route finding. They were doing it much, much faster than everybody else, and that probably represents the interaction. Okay, well now you see how SPSS does the analysis. You can see where it doesn't put anything in between hardly. It gives us the sum of squares, but that's about it. And all the information that's in the spreadsheet is all behind the scenes with SPSS. This just gives us the relevant findings and some basic information, but not the calculations that were made along the way to getting the sum of squares or the F score. Okay, now we've got our last step in hypothesis testing, generating our own sample scores with step 4, and now we want to draw our conclusions in step 5. So what were our conclusions in the end? First of all, there was no main effect for gender. On average, men and women took the same amount of time to navigate. There was a main effect for direction type. Map directions took longer to follow compared to route directions. So it took longer for people to find a destination with a map as opposed to a route in which you have directions. And finally, there was an interaction between gender and direction type. Men were faster than women with map directions, but women were faster than men with route directions. And so that's an expression of the interaction. So men do better with maps, women do better with routes. That's of this study when there's an interaction. Now, of course, this was all made up. I'm not so sure if these results would prevail with real subjects. This is a good example, I think, of taking the process all the way through for Factorial ANOVA. It's a very simple, straightforward example, and you can imagine once you get, more than 2 independent variables, and these independent variables have, say, 5 or 7 levels. You can see how complicated it could get to interpret what an interaction really means. And sometimes they really do get complicated, and sometimes, of course, these results occur by chance, and investigators are sitting around trying to figure out why a certain group did so much better than another group when actually it could have occurred by chance. And that's the big bugaboo with this procedure, I think, in general, is factorial analysis of variance leads to a lot of spurious findings that people sit and try to interpret. It's still better than trying to do inferences without probability. Okay, now in the next slides, we're going to review the assumptions of two-way ANOVAs and talk about another application of it. Okay, what are some of the assumptions of factorial ANOVA? Well, the assumptions of factorial ANOVA are the same as with univariate ANOVAs. Any other kind of univariate ANOVA or t-tests. And first of these is the populations have to follow a normal curve. Now remember, the F statistics are based on the assumption that the variables you're studying have a normal curve to them. That's how the probabilities are calculated, based upon that normal curve distribution. The populations have to have equal variances. So the populations you're studying, men and women, type of directions and so on, the variances have to be equal. They can't be unequal or skewed. And these assumptions apply to the populations that correspond to each cell. Now sometimes when you do a factorial analysis of variance, like we did actually with very small numbers, some of these assumptions can be violated. Generally, though, if you choose relatively large samples and they're randomly selected from populations, you'll satisfy all these assumptions. If you discover you have very unusual results, or you may have discovered some kind of sampling bias in your study when you actually conduct it, you may discover that you violated one of these assumptions. Now, some of the SPSS output will help you discover if the assumptions have been violated. There are certain tests that can be run. We're not going to get into those in this course, but that's one way of trying to figure out if you violated assumptions. In general, though, if you follow standard research design procedures, you won't violate these assumptions to the degree necessary to change the kind of analysis that you do. It may be true, though, that the populations you're trying to study don't have normal curves. They don't follow the normal curve distribution. In that case, you may rely on what's called non-parametric statistics, which we'll cover in a later section of this course. But that's what you do if you violate assumptions, is you transition to another kind of test that doesn't require this kind of distribution to make probability judgments. Now on to effect sizes in factorial ANOVA. We have a new concept of effect size. An effect size is an expression of the proportion of variance that's accounted for by the mean difference between groups. It's also called eta squared, or the correlation ratio. It's the proportion of the total variation of scores from the grand mean is accounted for by the variation between the means of the groups. And so here you have the formulations for it. You have an R squared, an effect size for every effect that you have. So if you have an effect for the column variable, or an effect for the row variable, or an effect for the interaction, then these are the formulas for calculating it. It's the amount of variability from the variability from the scores to the grand mean that's accounted for by the differences between the groups. So this represents how far apart the groups are as a reflection of their distance from the grand mean. So when you calculate this, you have small, medium, and large effect sizes. These are just conventions like I described before. And notice that they're the same conventions as we had for the one-way ANOVAs. Just for fun, compute this for the gender and direction study. Go back to the spreadsheet and calculate the ratios. They're very simple, straightforward to do, since the spreadsheet has all these sum of squares values already calculated for it. And you can see that the effect size for the I think it was the row variable that was gigantic. You'll see that's really, really big, and the effect size for the other interaction will be a little bit less than that one. And then there was one effect that had that was not statistically significant. I think that was the column effect, and so of course that effect size should be very, very small. Okay, but that's how effect size is calculated. That's how the magnitude of the difference between groups is calibrated, and it's a way of standardizing it across any kind of factor in the study. SPSS will also calculate effect sizes if you ask it to do so as an option that you choose when you run the analysis in the general linear model. It'll generate the effect sizes for each of the effects, for each of the factors in the study, and calculate that for you. Power in factorial ANOVA. The concept of power is the same as it is in the other procedures. The power is the probability of finding an effect when it's present. And this refers to a 2x2 table, a factorial ANOVA table. Notice that as the effect size goes up from small, medium to large, the power goes up. The probability of finding that effect goes up the bigger it is. And the probability of finding an effect goes up the larger the sample size. As you might imagine, if you have a large number of subjects, you more reliably measure the means that are in each cell. And so if there is an effect there, you'll be able to find it easier if you have lots of subjects. Now you can see, however, there's a certain point at which having lots of subjects isn't helping anymore. If you go over to the large effect size, look down that column, you can see that once you reach 30 subjects, having more subjects isn't really reduced any. You pretty much have the same probability of finding that effect at 30 subjects or 40 subjects or 50 subjects. And having subjects above 20 isn't really going to be adding much to the power level. Okay, so power varies with the size of the effect you have, and it varies with the number of subjects that you have in your study. Factorial ANOVA studies can get quite complicated. You can have multiple levels for your factors, so you can have 8 levels to your independent variables instead of just the 2 that we've been using. A study can have as many contrasts as there are variables, so you can have as many contrasts by interactions as there are variables in the study and levels. A study can have multiple dependent measures, and we haven't talked about that at all. We've just used one dependent measure in all of our examples. And when we get to the other chapters in this course, we'll cover some of the situations in which you've got multiple dependent measures. A study can have repeated measures, so you can have the same dependent measure measured more than once. So it's actually a different score that you're looking at between the first measurement and the subsequent ones. A common model for that would be something like a drug treatment study in which you measure, say, blood pressure before you give somebody a blood pressure medication. Then you measure blood pressure after you give it. Well, you have 2 measurements of the same dependent measure, and what you're interested in is the change associated with that. And you might have independent variables combined with it. So you might have people that are high and low blood pressure. You might have people with diabetes and people without diabetes. You might have other conditions that you want to study in your blood pressure medication. And so you combine all these into one big study, and you get all these interactions and repeated measures and all kinds of complicated stuff. I think sometimes these models get more complicated than people can actually reason about. And I've seen studies that were so complex that people had to break them down into components that made theoretical sense to them, and not just compare everything with everything. When you have multiple independent variables, that refers to the factors. So if you have 3 independent variables, like that, and they have 2 levels each, you'd have a 2 by 2 by 2 factorial ANOVA. And here's another example here where you have more than 2 levels. And here you've got 5 independent variables. One has 2 levels. 2 of them have 2 levels. 2 of them have 4 levels, and one has 8 levels. And you can frame this. You can combine them any way you want to, but they become a 2 by 4 by 8 by 2 by 4 factorial ANOVA. And you do this because you want to specify how many interaction contrasts there's going to be. So for every one of these multiplications, you're going to have that many interactions that you have to deal with. And as you can see, when you get to 2 by 4 by 8 by 2 by 4, you've got a lot of cells in your study. And see, sometimes what happens is people get significant findings in those situations. They've occurred by chance, and because they did find something, they have to interpret it, and often it's extremely hard to interpret why one cell in one of these studies came out significant and different than the other cells when you didn't have any kind of a priori theoretical reason for something like that to happen. And so you're sitting there thinking, gosh, why on earth did that happen? And people feel compelled to explain them with some new developed theory that just occurred to them while they were trying to ponder that, rather than simply saying, for all we can tell, this occurred by chance. At any rate, things can get very complicated, and we're going to deal with some complexity, some levels of complexity in the course. But to understand these things, it's important not to get too complicated, otherwise you get kind of lost. What we're going to go into is what happens when you dichotomize your independent variables to try to simplify things and the consequences of that. One way that people try to simplify complex factorial ANOVAs is by reducing the levels of the independent variables. So if you've got an independent variable with 8 levels or 10 levels, or even 6 levels or 4 levels, it's obviously going to make it simpler if you reduce those to fewer levels. The problem with that approach is that whenever you simplify your analysis by dichotomizing, and dichotomizing here refers to taking multiple level independent variable and reducing it to just 2 levels. The same thing happens when we reduce a 6 level independent variable to 4 levels, but dichotomizing is just the shorthand for referring to this practice. Well, when you do that, you reduce information in your independent variable. Now, that's okay to do if theoretically the independent variable should not be conceptualized with multiple levels. So, for example, you might have a scale that somebody's used and developed that's 6 levels or 7 levels, when actually over the course of using it, it's been discovered that maybe 2 or 3 levels describes the variance on the scale, and 7 levels just doesn't capture it. It's not unusual for people to want to have lots of levels for some reason in their measurement tools and their independent variables. They're thinking probably that they're going to be more discriminating if they have more levels, but sometimes they don't make any theoretical sense and they don't work out from an empirical point of view. Then it's okay to reduce the number of levels. But in general, you don't want to do that. You want to keep the number of levels at the number that's been set for the instrument or for the category, and you don't want to reduce it if you don't have to. Because when you reduce the independent variable levels, you're going to reduce the resolution of measurement, and so now you're going to put fewer categories when they ought to be put into more categories. And you reduce your power when you do this, so you reduce the chances of finding a significant result when it's actually there. And categorizing variables or dichotomizing them also lowers the effect size. So the magnitude of difference you're going to find between levels of the IV is going to be smaller now because the number of levels is now smaller. In general, you do not want to do this unless you have a very, very strong theoretical argument for doing it. Don't do it just to simplify your study, just because it seems so complicated to have so many levels for an independent variable. Keep those levels if they make theoretical sense, and modify your analysis procedures and just deal with the complexity. Think about things in a more complex fashion than trying to simplify them, and you'll make for much better discoveries when you do your studies. Okay, here's a complex factorial ANOVA that we're going to try here. We're going to try the repeated measures ANOVA model. It's a pretty common model used in studying drug effects and studying any kind of treatment outcome study. It's referred to as a within subjects factor because you have the same subjects being tested more than once. And so it's repeated measures. You have repeated measurements of the same subjects. And you would do this if you're doing a study where you're going to examine, like I described before, blood pressure before and after treatment with a blood pressure medication. That's a real clear model that uses repeated measures. Repeated measure studies are characterized by a correlated or dependent measurement. So the two measurements are not independent. So they're related to each other because you're using the same subjects. It's the same logic that applied to the paired or dependent measures t-tests. Remember, we did those a long time ago. It's just now we're going to be putting it in the context of factorial ANOVA, where you've got more independent variables. So here you have an example of a single factor, and this would be like what we had with one-way ANOVA, a change in illness before and after treatment. So this would be a change in blood pressure before and after treatment with a blood pressure medication. And then with multiple factors, with complex factorial ANOVA, you're going to ask the question, do males and females differ in change in illness before and after treatment? So now we're going to give our blood pressure medication to males and females, and we're going to study whether men and women differ in how they respond to the treatment. So here we have a gender as a factor, and that's a fixed factor. That's an independent variable by pre-post change in the dependent measure. And the pre-post repeated measurement is a within subjects factor. So it's a repeated measures factor, and we're going to be examining a different score to compare males and females. Now you can imagine this could get complicated too. You could have males and females. You could have different age groups. You could have different occupation groups. You could have different ethnic groups and things like that to find out if, say, males who are over the age of 60 who are Native Americans respond differently to a blood pressure medication than females who are Native Americans who are less than 20 years. So you can begin to imagine all the complicated interactions that might exist once you begin adding factors. However, it's very common to do what we've described here with males and females. Do they differ in their treatment response? Do they differ before and after treatment, say for blood pressure medications, for heart medications, things like that? That's a very, very common model. And we're going to go through an example that's similar to that. Okay, now we're going to do repeated measures factorial ANOVA in a study that I actually did a few years ago, in which I studied a new drug treatment for traumatic brain injury. Now here you see a depiction of a traumatic brain injury. It's a great, exciting-looking photograph. I don't know how they froze this woman's posture, right at the moment when she struck the board, but there was a photographer who just captured the moment right at the perfect time. Fortunately, in competitions like this, the boards are very flexible, and she was not severely injured by this, but it does illustrate a traumatic brain injury. Most traumatic brain injuries occur in motor vehicle accidents and falls. Those are the source of the severe ones. People get traumatic brain injuries all the time, though, from much milder things like sports injuries and simple, when you just bump your head. If you bump it too hard, you can produce an injury. Okay, and what I was going to do is study a new drug that's supposed to help the brain recover from these injuries. And so I want to go over some of the pathology of what traumatic brain injuries produce and how it might work. So I'm going to outline my theoretical model for the drug use. Then I'm going to talk about the study that I actually did in which I examined whether the drug worked to make things better after the brain injury. So let's just briefly go over what happens when you have a traumatic brain injury. This is all preamble for my theory about why my treatment should work. Okay, when you have a traumatic brain injury, a variety of things can happen. The first thing you have is direct impact, mechanical forces applied to the brain. So when you're in your car and you stop suddenly in an automobile accident, and believe me, you're stopping a lot faster than you ever have just putting on your brakes. You stop really suddenly when you hit something. Your brain moves forward inside your skull and impacts against the surfaces, the interior surfaces of the skull. So you have mechanical forces that are applied directly to the tissue that damage it. You have shearing injuries. As your brain is bound, it's very flexible and it shears around. It moves asymmetrically, and that causes parts of the brain to move against other parts. It doesn't all move together, and these shearing injuries will break blood vessels and damage neurons. You have hematomas, which are blood vessels that break and they produce a blood clot. That'll cause damage to the brain tissue. You have increased intracranial pressure. You have swelling that occurs in the brain, and this produces damage to the neuron. One of the things that happens, it's the end result of all these things, you have a disruption of neurotransmitter systems that are used by neurons to communicate. And so, as you may know, neurons are very complex, have a very complex biochemistry. They need to have an extracellular medium that's got all these chemicals in it that they need to use to function. And when you have these mechanical forces going, hematomas and swelling and so on, and even if the neurons are alive and reasonably healthy, they can't communicate with each other because the neurotransmitter systems have now been disrupted. And part of my treatment, or really my treatment, is geared toward trying to fix one of those systems that might be broken and make the traumatic brain injury associated with less pathology, less morbidity, and eventually less impairment of the brain after the person recovers. One way of scaling how severe a brain injury is by measuring the degree of coma that the patient experiences when they have their injury and they're in the hospital. In general, coma levels used as a way to stratify how bad the brain injury was. It's a very crude way to do this, but it's turned out to be reasonably good. It does cover most brain injuries. It probably is a good general tool for stratifying how severe an injury was. So if I want to find out how an independent variable like this interacts with my drug treatment, I would want to use this variable, this categorization, as a factor. And so I'm going to test if people with severe brain injuries, how well they do with my drug versus people with less severe injuries, and how well they do with my drug. So I want to establish a coma level for the subject and use that as a stratifying variable, an independent variable, in a multifactorial analysis of variance. See how that works in a second. This is coma scaling. Coma scaling basically scales how responsive the cortex is to stimuli. So if somebody responds only to pain, and usually that means you give them mild pain stimulus, like you flick their fingernails or rub their sternum, and if they respond, that means the cortex got that information about the pain and made a response to it. But if all they do is flail around and they don't get aroused and wake up, or don't say something, or do some more complex response, then that's better than not responding at all, but it's an indication that the cortex is still quite impaired. Then if somebody responds to pain or verbal command with a meaningful response, that indicates the brain is able to construct, a very complex, meaningful response. So even if it's the patient just calls out, stop doing that, or that hurts, that means the language centers are working. The language mediating parts of the brain are actually formulating a response. And then you have levels higher than that where people basically are more or less normally responding, but they fall asleep very easily. They become somnolent. And so it's important to keep people awake sometimes, because you want to find out if they're going to get worse, and the only way you can do that is if they stay awake. At any rate, somnolence is a high level of response. Somnolence means that they're responding to pain and verbal command, but they're just falling asleep easy. That's the sort of highest level of coma. That's almost just like the sleep you experience every night. And then you have people that only respond to pain, or who don't even respond to pain, and that's a really low-level response. That indicates the brain is not working at all. The drug that we studied was called cycloserine. And cycloserine works at the synapse of a neuron. And I'm not going to go into a lot of detail about this. Suffice it to say that it helps parts of the synapse work better. And if you're in traumatic brain injury, all these synapses between cells are disrupted. The synapse is the connecting structure that connects between two neurons, and it connects using neurotransmitters that are secreted across an opening. Well, if the neurotransmitters aren't there, if they're blocked in some way, or if the postsynaptic neuron receptors aren't working, you can have all kinds of disruption of function because these cells can't communicate with each other. Well, here you see depicted an axon of a cell off in the distance, interfacing with the dendrite of a cell up here in the front. And what happens is when that cell off in the distance wants to stimulate this one, it secretes neurotransmitters in those little vesicles down there that make the postsynaptic neuron respond. And what this drug is going to do is facilitate that process for one neurotransmitter system that's affected in traumatic brain injury. So here we see another schematic that depicts the synaptic function. And what cycloserine is technically a partial NMDA receptor agonist, and that means that it works as a partial facilitator of the NMDA receptor. Now, NMDA receptors have been implicated in memory function and all kinds of things. NMDA receptors are often overstimulated in traumatic brain injuries, and this causes calcium to flow into the cell and the cell to die. So if we can block or partially block the NMDA receptors in traumatic brain injury, we might be able to facilitate recovery later because the calcium is not going to go in there and kill the neuron. Or if later, after the neuron has recovered, we can, through our partial agonist, actually make the NMDA receptor work better, we might facilitate memory function and the general function of the cell after the injury and during recovery. So that's our hypothesis. So that's our research question. Will cycloserine improve recovery from traumatic brain injury? And we have a theory that explains why that might occur. And so now we're going to go out and collect data to try to test this hypothesis that cycloserine will help people recover from traumatic brain injuries. Okay, here's our research design. We have a repeated measures factorial ANOVA. Our dependent measure is going to be memory scores. So we're going to find out our measure of recovery from traumatic brain injury. We're going to measure using a memory test. And the dependent measure is our scores on that test. Our independent variables are treatment versus control group. So you have treated versus control subjects. And we have coma level as an independent variable. Our repeated measures are pre and post drug treatment. So our repeated measurement is going to be memory scores pre and memory scores post drug treatment. Now these data are already stored in a variable set called trauma.sav. This is an SPSS data file, and we're going to use this data file to analyze the data. So you need to go, after this presentation, this slide is done, go to the website, download trauma.sav, and it's probably called trauma dataset, something like that. We're going to analyze for main effects for the independent variables with repeated measurements, and we'll plot the results and things like that. I'll show you the results. I'll show you the steps like I did before, but this is basically what the menu we're going to follow here to analyze the data. The first step, though, is to download the data set and open it in SPSS. Okay, this is what the data should look like when you open it up in SPSS. Again, if it doesn't look like this, you have trouble opening the data file, then you've got to check you have the right version of SPSS and so on. But when you download the trauma.sav file and double-click on it or open it up in SPSS directly, you should see the data like this with the treatment variable. And treat indicates a treatment group or control group. That's 1 or 2. You see the age of the subjects. You see their coma levels. You see their pre-drug memory scores. That's what pre-drug is. Then you see their post-drug memory scores. And we're going to analyze this in repeated measures, multifactorial ANOVA. Okay, the first thing we're going to do is not the factorial ANOVA right away. The first thing we're going to do is just to see what the means of these variables are like, because that'll help us in interpreting the ANOVA later on. So to get the means for these basic variables, you go to the Analyze menu, choose Analyze, go down to Descriptive Statistics, and choose Descriptives, and then in the next dialog box, pick that you want to see the means. You probably have done this before. I'm sure we've done this before in 364, but basically you want to see the means for each one of these variables, basic descriptive statistics, the mean, standard deviations, and things like that, just to see what they look like. And we'll see that on the next slide. This slide shows the basic descriptives for these variables. And we would just want to look them over to see if they look right. And we want to see what kind of comparisons we can make just by eyeballing this. Okay, so you look at the age of the subjects. The mean age is 29. The minimum is 18. The maximum 56. That's the right age range for traumatic brain injury patients. The pre-drug memory score is an 81. That's the average, is an 81. The post-drug memory score average is 90. So we can see their memory scores improved over time. But we don't know if this improvement didn't occur by chance. That's why we have to do a statistical test. Because obviously memory score is going to change from time to time if you test people more than once. And we want to find out if these scores have actually improved. And finally, you see coma level there. It ranges from 1 to 5 with an average of 2.9. Now that indicates there's variability on the coma scale. In a lot of trauma studies, there isn't sufficient variance on coma. That means that they either have very mild cases in their samples or very severe cases. And this shows us here that we have a nice range of coma level and a nice range of severity in the study. Now we're going to do the repeated measures ANOVA. Factorial ANOVA. And so what you do is you go to the Analyze menu, choose General Linear Model, Repeated Measures. Now we used univariate before. Now we're going to choose Repeated Measures. We have to set up the repeated measures contrast. We need to tell the program what the repeated measurements are. In this case, it's going to be pre-drug and post-drug. But the first thing we need to do is choose that option to start the repeat measures specification. Okay, here's the next dialog box that appears. So when you choose repeated measures, you get this dialog box here. The first thing you want to do is give the within subjects factor a name. And here I've just given a name pre-post, so I type that in. I type in the number of levels, which is 2. So we have a pre and a post, so that's 2 levels. The next thing I'm going to do is click the button Add. And when I click the button Add, it will fill in the pre-post designation there for the within subjects factor. Then the button down below that says Define will light up, and I can then click that and go on to the next dialog box. Well, here's the next dialog box that you'll see. Now in this dialog box, we're going to set up the within subjects factor and the between subjects factors. We've already specified there's going to be a pre and post drug repeated measures. So what you have to do, all these variables that you see on the page now in the dialog box were originally in that window in the box on the left there, where age and coma are now. So the first thing you do is click on pre-drug as a variable, and click the right arrow to put it in the window there on the right. Then click on post-drug, and click on that arrow again to put it there on the top window on the right, so it looks like it does right here. So that's telling the program that pre-drug and post-drug are 1 and 2 in order for the within subjects factor. They are the within subjects variables. Then what I've done here for my first pass at this is click on the treat variable and put that in as a between subjects factor. So remember, the treat variable is treatment group or control group, and so I'm going to test whether the treatment group and the control groups changed over time. Now my within subjects hypothesis is that the treatment group changed over time and got better, but the control group stayed the same. And so I'm going to test that hypothesis with this analysis. So when you have the dialog box looking like this, click OK, and then it will run the analysis. Okay, when you run the analysis through SPSS, you're going to get lots of tables that you will not understand. And unfortunately, for a class like this, SPSS was designed for professional level statistics, and it's got all the extra stuff in it that normally would come out with an analysis like this. Most of that we're going to ignore for right now. And what I want you to do is go through the analysis, go through the output, and pick out the two tables that I've shown here. The first is called the tests of within subjects effects, and the second one is called tests of between subjects effects. And make sure you got the one that looks like this. Now you can see in these tables some things you recognize. There's a lot of things in these tables that we're not going to pay attention to right now. And it looks much more, the language is much more complicated and esoteric than it should be. The basic ANOVA table for within subjects analysis. So let's look at the within subjects effects first. Now, within subjects refers to the pre-post change over time in the memory scores for the trauma patients who got treated and those who didn't. Well, if you go down the table, the first part of the table here at the top where it says pre-post is just testing whether there was a pre-post change. So is the within factor, did it show a significant result? And as you go across here, just look at the top row. And you notice it says type 3 sum of squares. Well, that's sum of squares, just like we learned about before. Those are the distances of the sample scores from the grand mean and so on. And here you see there's a sum of squares of 1,188, degrees of freedom of 1. So remember, pre-post is just two conditions, so degrees of freedom would be 2 minus 1. The mean squares is the same because you divide by 1, you divide by the degrees of freedom. And that results in an F ratio if you divide 1,188 by what's referred to down there as the error. Now see, the error is the within cell variation that we learned about before. But if you divide that by 38, 38.198, you'll get an F score of 31.105. An F score that high of 31 will be significant, almost always. And you see there the significance level, the P level associated with that is 0.000, and again that would be reported as 0.0001. So it's very unlikely that this change that we saw over the pre-post measurement score, the memory scores, could have occurred by chance. So that difference that we saw, I think, was something like it went from like 81 to 90 something. That was did not occur by chance. It'd be very unlikely for something like that to occur by chance. So that's indicating to me that the trauma patients are improving, they're recovering, and so the change pre-post is a reflection of that. Now if we go down to the next variable, or the next contrast, we see pre-post by treatment. Okay, now it's going to do a repeated measures assessment of pre-post by whether the subjects were treated or not. And again, go across the first row. and you see that the interaction between those two things is not significant. So the F over there is 1.226. That's not very high. And the significance level, the probability level that SPS is giving us is 0.278, which is way above 0.05. And so it's probably likely that whatever differences that exist there between the treatment group and the control group occurred by chance. So it doesn't look like the treatment, the drug treatment, improved memory scores over time. Now finally we go down to the between subjects effects, which is just going to test whether the control group and the treatment group did better. And if we go across there, we see that F is 3.30. The significance level is 0.08. And that also is not very good. It's a trend. It indicates that the treated group may have done better. See, this is testing the treatment versus control group regardless of the repeated measures factor. And we see it's a trend. So it looks like the treatment group maybe did a little better, but it didn't reach 0.05. And so I still have to conclude that the treatment likely did not have an effect. I can support my research hypothesis. And so I have to, I can't reject the null hypothesis and support my research hypothesis. This result could have occurred by chance, and so I have to leave it at that. Well, that's a very long presentation for Factorial ANOVA. It's the longest one so far in the course. It's probably the longest one that we're going to have. Factorial ANOVA is a difficult thing to present. There's a lot of complexity to it, and it steps up in its complexity. So I've tried to map this out carefully so that it goes from the simple examples to the more complex ones. And of course there are more complex ones than even the ones that I've shown you. But just to get you used to the idea of a factorial ANOVA as opposed to just univariate ANOVAs and one-way ANOVAs, to start to treat multiple independent variables as if they have interactions. That's the most important thing about this. This lets me study interactions, whereas before all the other methods were just showing me single main effects one at a time.